And I'm just going to pretend like you did and move forward. Okay, so now is when we go over the forces in the atmosphere. There's going to be 5 main forces in the atmosphere. Okay, and the first one, and the one that I really kind of go over pretty well, because to me is probably one of the most important forces in the atmosphere, is going to be called the pressure gradient force. Okay, pressure. Well, we already know pressure. We kind of already understand pressure. We've already went over pressure. We went over ideal gas law, and we went over things like that. So I'm going to kind of skip that word, what that means, pressure. But gradient, what does that mean? The gradient is the rate which something changes over a distance. So, I'm going to find my cursor here. This actually is an island in Hawaii. This is actually the Hawaii Island, and it's the big island, which has the volcano on it. Now, I'm going to kind of bring it to something that hopefully you guys have seen more of, because a lot of people don't see like weather maps if they're not a meteorologist, but they would have seen something like this, which is a topographic map. A lot of people see that in like high school or something. So anyway, this is like the island of Hawaii with the volcano on it, and everything is good here. But the gradient is going to be the rate at which something changes over a distance. If we're looking at, from here to like here, okay, on this map right here, what we're talking about when we're talking about the gradient is the change of height over the distance, right? We know this is the volcano, so it's going to be pretty high up in the air there. And down here is going to be the base of the volcano, so it's going to be kind of closer down to sea level. So we know that there's quite a bit of a difference in height. This is going to be a steep hill right here. We are not going to want to probably try to hike that unless you're like a real serious hiker. It's definitely going to make us winded. We're going to, maybe need to get hiking gear out. I don't know. Like, I'm not really looking at the numbers. I'm just saying that I know by looking at these lines that this is a real steep gradient. Okay, this is going to be quite a bit of a trek from the base of the mountain to the top of the mountain. Okay, now the reason why I know that is because I'm looking at the contours, which is going to be, lines connecting of equal value. So this contour says 8,000 all the way around. If you connect that line, every single spot on there, if you go on one side of it, it's going to be lower than 8,000. On the other side, it's going to be larger than 8,000. Cool. All right. What does that mean for us in terms of weather? So this is going to be a weather map with lines of pressure, basically. And we can see, I forgot a point here. What I was going to say is the reason why I knew that this was a steep gradient here, okay, is that the lines are close together. So where the lines are closer together, that means you're looking at a steeper gradient than when the lines are further apart. So like right here, we might need to get some climbing equipment out. Oh my gosh, this is going to be like a real steep hill between the base and the top there. I mean, look at that. They're really close together, right? But like over here, like between here and here, there's a lot more room for each line. They're a lot of space. They're spaced further apart. So that means to me that it's going to be less of a slope. So I could probably like trek that, right? I could just take my dog Argos and we could just kind of walk along and, we're going to be good to go. Okay. Whereas here, I don't think Argos could make it up that part. You know what I'm saying? So that's how I knew. I knew by looking at the lines. I could see how close together they were. And that meant to me that it was a steeper gradient. So now going back to the weather map, we know we can look at like between here and here because those lines are close together. That means that it's a steep pressure gradient. That means that there's going to be a large force going on. That force is going to be strong. Okay, that vector is going to be longer than it's going to be if it's between like here and here. Here and here, they're not very close together. So that means that the force isn't really that strong. Force is not with you. Right? So we can look at these isobars, we can kind of visualize it, and we can kind of say, okay, well, I know that the pressure gradient is going to be stronger here, and it's going to be weaker over here. The other thing is that they always push from high to low pressure. I think I went over this before. If we let a bike tire out, like open it up, or what I'm calling unscrew the cap thing, then if the air was to go from outside to inside, we would think something was odd. Something was wrong. We weren't on the planet Earth, right? We know that it would go from inside to outside, like if you untied a balloon or something. That's because the pressure is higher inside than it is outside. So it's always flowing from the high pressure to the low pressure. So what that means is that the pressure gradient force. Now remember, when we're talking about all these things, we're talking about the force, not the wind. I haven't gotten to the wind yet. This is just the force. Okay? So we're going to draw the vector always perpendicular. It's always going to go straight through. There'll be a 90-degree angle between the contour line and my vector line. And like I said, they're going to be stronger when isobar. Isobars is going to be the name, by the way, for a contour that connects lines of equal pressure. Okay, that's the actual name for it. We can use the word isotherm if we're talking about temperature gradient. Or we can, use different terms depending on which variable we're looking at. But an isobar is going to be the name for specifically looking at pressure gradient. All right. A note about their pressure gradient force is going to be the only force in the atmosphere that can start an air parcel in motion. No other forces can actually start the parcel to move. It's just, some other one's going to deflect it in one way or another once it's already moving. But the pressure gradient force is unique because it starts it. This is why I consider it the most important force, because the rest of them are just going to act upon it. This one actually starts it. So I would know that if I was you. All right, so we were talking about vectors, right? These lines that show magnitude and direction. All right, like I said, they're going to be perpendicular to these isobars, so they can go straight through it, all right? They go from high to low pressure, and then you're going to draw them longer the stronger the force is. All right, so you see over here where these isobars are not very close together, the line is shorter. But over here where the isobars are closer together, you draw it longer because the force is greater. All right, so now we're going to move on to the other forces. Now, gravity. Gravity is going to be another force. All right, there's a strong vertical pressure gradient force due to the decrease of pressure with height. So if you think about it, there's lower pressure on top of higher pressure, right? Because the pressure decreases as you go up in the atmosphere. So why don't air parcels experience a force which try to accelerate them up? Why doesn't air constantly just try to rise up and that's that? Well, because they're in balance. They're in balance with gravity. Now remember, when forces are in balance, there is no acceleration. Okay, so this is an important term here, this hydrostatic balance. All right, this is going to be the balance between the pressure gradient force and gravity in the vertical direction. All right, remember it's in the vertical direction because obviously gravity is not going to affect an air parcel that's moving horizontally. I mean, it might a little bit, right? But they're in balance, so it wouldn't really affect it. And that's where there's no net acceleration. We don't have to worry about that. We can kind of move forward and know that the air parcel is not going to rise due to pressure gradient force. Now, it might rise due to instability. It might rise, due to, positive buoyancy. It might rise due to topography, but it's not going to rise due to the pressure gradient force in the vertical. All right, now, I have actually never taught this specific concept online before. Usually I take a globe in the classroom and I have somebody kind of draw on it while I'm having somebody else spin the globe. This one, I'm just going to kind of describe it, and I'm going to, this is a link, and I think I'm just going to click on it and we're going to watch this together. Okay, is how I'm really going to move forward. If you're struggling with this concept, there's many YouTube videos on this specific concept. You can read it in the book, and you can always Zoom me. You know what I mean? Get a hold of me, and we can have a Zoom call or something. All right, so this is going to be forces, the Coriolis force. The Coriolis force is a force that deflects objects that are already in motion. So remember, the rest of the forces other than pressure gradient force are going to be objects already in motion. It's going to basically move it in some way or another. All right, so the Coriolis force deflects objects to the right in the northern hemisphere and to the left in the southern hemisphere. Now, because it goes, one way in one hemisphere and the other way in another hemisphere, then that means where they meet at the middle, which is the equator, there is no Coriolis force. All right? Remember that there is no Coriolis force at the equator. This is why big storms will not pass the equator. All right, I've seen movies where they show like big hurricanes passing over the equator. That's so false. It would never happen. There is no Coriolis force, so it wouldn't even be possible. Okay. The other thing to remember about Coriolis force is it's going to be stronger the faster the object is moving. Okay, so let's watch this video. This works here.
Draymond Green, what's up, brother?
That's cute.
By the way, you lose. Ooh. Well, listen.
This is my Simpson video. I'm gonna post this for you guys. Actually, I'm not gonna make you watch it right now. Cut that out. Okay, so why don't we notice this force in our daily lives? All right, why don't we notice, something deflecting every object in the northern hemisphere and every object is moving in the southern hemisphere, like our car driving down the street or a ball that we might throw? This is because we live on a planet that is round and rotating. This is another thing I would know. Now, this is where I'm going to show you here what I'm talking about.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis force, whereby, to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
Here's another one. So they can throw the ball and just throwing it back and forth, it just normally just goes in its regular straight path. Now you can see that it's still going in a straight, you can see as they're moving though, it's still, see the problem is they're still going in, the ball is still going in a straight path. It's the fact that they're actually moving away from the path. See, if you look at it this way, you can see that the ball's still moving in a straight path. It's the fact that they're actually moving away from that straight path. So it's going to appear, if you're not looking at it from their perspective, it's going to appear like it's actually going to the right. So it brings me to an important concept. Coriolis force is deflected to the right with respect to the air parcel. All right, you got to make sure that you're looking at it from the air parcel's point of view. If you're looking at the air parcel and it's going straight forward, then it's going to be deflected to the right. It's not going to be deflected to your right. It's going to be deflected to the air parcel's right. Okay, so imagine that ball is like an air parcel. Okay, see, it's deflecting to the ball's right, not to the guy on the right's right, because then that would actually be his left. So you got to look at it from the ball's point of view. Yeah, there's a Wilson ball. See, it's actually moving straight. So that's the reason we're round and we're rotating. And since we're on a big globe that's moving, then even though the air parcel is actually moving straight, the globe is actually moving underneath it. And so it actually appears to us, if we're looking down at it, like our satellites looking at, things and stuff like that, it's actually deflecting to the right. Now remember that this is dependent upon speed. Since it's dependent upon speed, then that means that anything that's going fast, okay, and is large and has a big enough path is going to be deflected to the right. Things like rockets, things like missiles, snipers actually have to be concerned about the Coriolis effect. People like that, but not a basketball player. Okay, that's not, the basketball isn't going to be, whoa. Sorry, I saw this playing in the background there. Okay, so that's not, basketballs, if I threw a ball at you, when we weren't like on a rotating thing. Anything like that, like, you know, dodgeball, I guess, you know, that idea. It's not a big enough, I'm gonna say, area for it to actually count. It's not going fast enough. And that's also why, you know, and the Simpson video that I was going to pull up for you guys here in the beginning, that Simpson video shows you this whole thing about the toilet actually, like, flushing, because Bart Simpson calls and asks, you know, somebody in Australia to flush the toilet. And they say, oh, it's going the opposite direction, because a lot of people have heard of that. But actually, toilets don't go in opposite directions in the Southern Hemisphere, and that's because it doesn't go fast enough and it's not going far enough. Okay, so if it was to go in the opposite direction, it's because of the way that the plumbing is. It doesn't have anything to do. So when I show that video in class, I usually say, don't get your news from The Simpsons, right? Although they seem to be right a lot more times than you would expect, right? Kind of strange, huh? Anyway, so we'll leave that at another point. But normally speaking, don't get your news from The Simpsons. Okay, another force here is going to be centrifugal force. This force is basically just like this little merry-go-round thing that we've all seen when we go to amusement parks, right? It's going to pull all the people out from the center. That's what the centrifugal force is. So this is going to basically affect objects that are rotating, like tornadoes, hurricanes, cyclones, anticyclones. Remember, cyclones and anticyclones are going to be different names for high and low pressures systems. Always result in a force that pulls outward from the center. So you can see I kind of have a little crude drawing here for that. All right, and then the last force here is going to be friction. I think it's the last force, yeah. Friction. Okay, so we can only act to slow down the wind. It doesn't deflect it in any direction. It doesn't do anything else. All it does is just slow down the wind. Okay, although, remember, slowing down the wind actually can change the direction. We'll get to that in just a moment here. The force is actually going to be, the friction force is going to be stronger for faster motions, is stronger near the surface, and effectively zero aloft. Now, why would that be? It's actually stronger near the surface because of trees and buildings and billboards and cars and people and anything that you might have at the surface. We all live down here, and this is where everything is, and all that stuff actually is going to cause more friction on the air, and it's going to act to slow it down. Where aloft, we don't have all that stuff going on, so it's just more able to move freely without having anything to try to slow it down. It's also stronger over land than over the ocean for the same reason. Ocean it's flat. It doesn't really have anything on it except for maybe a few boats, but not like, you know, a forest or something. Okay, so these 5 forces. As it turns out, humans are horrible at keeping track of 5 things at one time. All right, could you really try and keep track of all 5 of those variables to figure that out in your head? It would be difficult to do. So it's actually going to be better if we can think of situations where one force is so small it can be ignored or canceled out. Right? We love that when we're doing math, don't we? Where we can just like draw the line through, you know, the fraction, because we're like, sweet, that one can just be canceled out, right? Same thing with these forces. If we're talking about the forces, it's great when you can just draw the line through it and be like, okay, it cancels out, I can ignore that one. All right, now here's the second set of group questions. I want you guys to try and answer these. I guess this is the end of lecture 1, and look forward to lecture 2.